Hello, everyone. Good morning. That's a pleasure for me to be here and to talk a little bit about my research, but not so much about the research itself, but rather of a methodology we use um, to characterize anaerobic processes. So my background is on wastewater treatment processes. I have been doing a lot of research on anaerobic treatment, optimizing nitrification, denitrification, and so on. But in the last years, I have moved more to the anaerobic treatment technology. Well, I'm sure that most of you are familiar. Anaerobic treatment has been with us for a very long time, but in the context of it's gaining more attention in the last years because of the context of this circular economy, the way of treating wastewater in a more sustainable way, trying to recover as much as we can the valuables of this wastewater. And for that, anaerobic digestion is a perfect technology. You can treat many substrates, not just liquid wastewaters, but also kind of solid substrates. The thing that they have to have in common is the organic matter you have in this wastewater that has to be biodegradable anaerobically. And then the process itself, I find it quite interesting. You have a different consortium of microbes there between bacteria, archaea. They need to try to break down the substrates, keep reducing it until ending these complex substrates to the more reduced form of carbon, which will be methane. And methane has, can be biogas. It has a lot of energy content, so you can get energy out of it, electricity, fuels, and more recently, you can kind of clean this biogas and get more pure methane that you could use to get added value compounds. So that's I think that's a research line that will pick up in these years, at least at the European level. There are some calls going into that direction. And then a part of the gas you make during this reduction process of the organic matter, you also get this digestate that is what is the leftover on your anaerobic digester. The mainly are this piece of material that contains a lot of nitrogen and a lot of phosphorus, so you can use it as fertilizer. So very interesting process, but today I'm not going to talk about the digestion process itself, but rather of these biomethane potential tests that are very useful. It's a very simple methodology that when it's well applied, you can use it not only to determine this specific maximum methane production potential of a specific substrate, but also you can get it, you can use it to get other insights into your process. So this test has been commonly applied since, I would say, the beginning of research on anaerobic treatment technology. And that's because it allows you to test not in your anaerobic digester, but rather in a batch test, this methane production potential of any substrate, and also what kind of to get the parameters, the kinetics, so you can also run then later on your anaerobic digester depending on the parameters you have been gotten there, and also can give you an idea about potential inhibitions of the substrates, and that's very interesting. So damage your anaerobic reactor. There has been many different methodologies applied in different labs during the years. And that was a bit of a mess because depending on how you run your BMP test, you can get different results, obviously. And because of that, by 2015, it was this workshop that took place in Switzerland, where the key groups working on anaerobic digestion meet, and they were discussing for a couple of days of the different methodologies used to approach this BMP test. And as an outcome of that workshop, it came this paper that was published in Water Science and Technology from Holliger and co-authors. That's a very useful paper that is a must read if you want to conduct this BMP test. And that gives you some indications of how to do this BMP test in a standard way. Some considerations you have to take into account. I just listed here the key ones. All the tests must be carried out as a minimum in triplicates. If you can have more, even better. Control tests are needed, and positive controls with cellulose. Cellulose is a substrate that you know what is going to be your specific methane production at the end of the test. If you can do them, is also, you have to also to consider that. Also, the BMP of the substrate is determined by subtracting the methane production of the plants. So you can have an inoculum that has some methane production, and that needs to be subtracted from your tests. And the duration of the BMPs cannot be fixed upfront because it will depend a lot on your substrate. So now we know that the standard way of finishing a BMP test is when the methane production during the 3 consecutive days is lower than 1% of the accumulated volume of methane. Also, you need to use an inoculum as fresh as possible. That's, you go to an anaerobic digester, and then if you can, you set up your BMP test. Normally, or sometimes, depending on how your full-scale anaerobic digestion source is operated, it can have some residual organics there. So, and then you can have an inoculum that has some endogenous methane production. So here, it's good that you pre-incubate your inoculum at the same temperature you're going to run your test in order to get this methane production being kind of exhausted or minimized. And that has to be done for a maximum of 1 week. If you have an inoculum that still after 1 week, it produces a lot of methane, you should go to another anaerobic digester and try to get another one. And never, of course, keep the inoculum in the fridge. And that's because this kind of microorganisms are used to work on mesophilic conditions around 34 degrees. Some digesters work at thermophilic conditions, 55 degrees. So imagine being a microbe and being stored, moving from that nice temperature to 4 degrees. That inhibits them a lot, and most of them don't recover. So never keep the inoculum in the fridge. Okay, how we do BMP test at ICRA? So we started a few years ago, and we started with the basic methodology that many labs have. So lots of different small bottles. There are around 200 mils, these bottles. We put them in an incubator that we can set the temperature. We normally run at mesophilic conditions, but we have been also performing tests at thermophilic conditions. We normally use shakers inside these incubators because that's, well, it depends a lot on your substrate, but sometimes if you don't move your BMPs, the gas production you get is not homogeneous on the day. So for us, our experience is better that you shake a little bit your bottles while you are conducting the BMP test. That doesn't mean it has to be shaking all the time. So it can be, I don't know, maybe 1 minute every 10 minutes, every 15 minutes, and so on. Then we have a gas pressure sensor, just to monitor the methane or the gas being produced. At the beginning, you will need to monitor it every day in order to avoid that your bottle explodes of the pressure. But when the substrate is being consumed, you will get less methane production, and therefore you can spare your monitoring of the pressure of the gas. And then you can just quantify if you have a GC available in your lab. That's perfect. So you can get daily methane concentrations. In our case, our GC is common at all ICRAs, so we have to share it with other groups. And therefore, what we use was this methane sensor just to get a reading on the methane concentration of our test. That's a good methodology. You can run multiple tests, but even 50 bottles you can have on one run. But of course, you need to check the pressure and release the pressure in a daily basis, mainly at the beginning of the exponential phase. And then you also need this measuring of methane. So that requires a lot of manpower. 2 years ago, we bought this fancy gas in the upper instrument from Bioprocess Control. And I say fancy, maybe because of the cost of the equipment. Well, it's not that much, but it costs us around 24,000 euros approximately. But is very nice. It allows you to run less experiments. It's only 12 bottles. You can see them in the background over there that are connected to, they have a stirrer that you can set up the speed of the stirrer, and then the gas is transferred to some glass bottles that you cannot see here in between the water bath and the things you see in the front. In these glass bottles, we have sodium hydroxide, so that removes the CO2 of the biogas. And then the remaining gas goes to these devices here in the front that are nothing else like counting the methane being produced. And with that, you can get an online monitoring of your methane production from the 12 bottles. So you actually have a computer attached to that system, and you can follow exactly how methane is being monitored. And that's very good in terms when you want to play a little bit with your experiment, adding more substrate, taking samples, whatever you want to do. The limitation, of course, you only can have 12 tests in parallel. Well, if you have a lot of money, you can get more of them and have more. But and then what we normally do with the BMP test, we try to enhance these experiments in order to get more insights into the process, in order to get more scientific information, so then you can lead to a publication. And for that, at ICRA, we have a lot of equipment to monitor micropollutants, pharmaceutical compounds. So we normally combine these BMP studies with taking samples for analyzing pharmaceutical compounds offline. And we have been doing that in the BMPs, using the BMPs as a black box, so meaning that we take samples at the beginning of the test, then we set up the BMPs, we close the bottles, and we don't open them until the end, until the methane production is stopped. So then we can know what has been happening between beginning and end, but not in the middle. And then we have also using another methodology to get samples from once the BMP tests are running. And then we also like to explore our microbial communities. That's a biological process. So knowing who is there and how this community is changing give us a lot of information about the effect of your substrate of anaerobic conditions into your microbial community. So for that, we extract samples of the biomass. You can keep them at -20. And then once you finish your BMP, you decide which samples you want to extract the DNA from, and then you can send it for sequencing. Okay, and now I would like to give you two examples of different BMPs we have been conducting. Example one is using complex waste as substrate, and this test originally came from a requirement from an industry that wanted to know if the substrate they were having was able to be anaerobically digested, and if it had some inhibitions and so on. So we used that to start our BMP research, but then from then on, we have been also conducting BMP tests to fundamentally understand other processes. That will be example two. But let's start with example one. That we use, of course, manures. Manures are a perfect substrate for anaerobic digestion. We have been working with solid manures, such as poultry and cattle manures, but also with pig manures, which is more liquid, although here I just will present results for these two substrates. And then we have been also working with slaughterhouse wastewater. This wastewater maybe is less concentrated than the manures in terms of nitrogen and organic load, but still it's considered a nutrient-rich wastewater. Both have in common these high amounts of organic matter that can be anaerobically digested, and also a lot of nutrients that you need to take into account, especially the ammonia. I will come to that later on. Okay, we set up the experiments with these manures because we had to run multiple tests with the two manures simultaneously. We use this methodology of multiple bottles. Anaerobic sludge, we use it from a local digester. Substrates were the cattle and poultry manures. And here in this table, you can see a little bit the characterization of these two substrates. The most interesting here on the characterization for us was the total COD content. That as you can see, the poultry manure was very, very concentrated. Also the volatile solids that you need to consider when you want to set up your test, because normally tests should be performed at an inoculum to substrate ratio of 2. And then the ammonia concentration we had was quite high already in the inoculum and in the cattle manure, but was 1 order of magnitude higher in the poultry manure. And that gives us some problems during the BMP tests. The tests here were conducted at mesophilic temperature, 35 degrees, and thermophilic temperature. We wanted to see if with thermophilic temperatures we could get higher methane production, and also in terms of pharmaceutical removal that we also monitor in this case, some reports have been reporting that higher temperatures enhance these pharmaceutical removal compounds. Okay, and here is the two graphs we obtain in terms of a specific methane production for the cattle manure and for the poultry manure. And we can see here the two different temperatures, the mesophilic conditions of 35 degrees with black spots. What we observe here is as soon as we set up the BMPs, as soon as they started to produce methane. That was somehow expected because mesophilic conditions applied here were the conditions of the inoculum. So that inoculum came from a mesophilic digester, so they were used to that temperature, and therefore they started to produce methane straight away. So normally what we do with the methane results is we feed models used for this kind of processes in order then to get the parameters, the kinetics. And for when you get this type of profile, you can use a first order model. And then you can know the maximum specific methane production, the hydrolysis rate, etc. When we use when we applied the BMP test at 55 degrees, what we got was this kind of lag phase. Let's see if I have an animation. This lag phase period that took well, around 5 to 7 days. No, less, 4 to 5 days. And we believe that was because the inoculum was adapted to mesophilic conditions, and therefore once the inoculum was put at 55 degrees, not all the microbes can operate at 55 degrees. So some of them have had to adapt. And therefore we had this lag phase. When you have that in your BMP test, you need to use this Gompertz model that can model this kind of lag phase at the beginning. And then an interesting observation we had here is that the methane production stopped at 55 degrees when it reached around 200, as compared to the same substrate when run at 35 degrees. And that's because it's related to the amount of ammonium we have in the system. So the ammonium is in equilibrium with ammonia, depends on the pH. A higher pH, more equilibrium will be moved to the ammonia, and also depends on the temperature. And therefore, once you have higher temperatures, your pH is changing, is going up across your BMP test a bit, so you can have more accumulation of free ammonia, and free ammonia inhibits the process. And therefore, that's the reason we got this lower specific methane production. So for these particular substrates, we recommended to use or to treat them at mesophilic conditions. Okay, then as I mentioned before, we took samples from the pharmaceutical compounds to analyze them at the beginning of the test, and then at the end of the BMP test, as soon as the methane finished the production. So we open the bottles, we mix the triplicates, and then we measure the concentration of pharmaceutical compounds we had. For the cattle manure, we detected less pharmaceutical compounds compared to the poultry manure, but in general, we saw that anaerobic treatment provided good removals. Have to say, here we call removals, but we did not analyze in this test the accumulation on the solid phase. So we talked about removals of the liquid phase of the compounds. And then we also observed that higher removals were detected at thermophilic conditions. So higher temperatures enhance the removal of some of these compounds. And of course, as I mentioned before, we would like to know who is there and who is doing the job, and how these microorganisms are changing during your BMP test. That will be also an indication of how they will behave in your anaerobic digester. So here we have a heat map of the microbial community present. And what we can see straight away, as expected, as the microbial community of the inoculum was very different from the microbial communities present in the poultry and cattle manures. And that's expected because the inoculum is treating waste activated sludge coming from a municipal wastewater, and the manures are mainly, we will find mainly bacteria that is found in the guts of the animals. But when the process is evolving and the anaerobic inoculum started eating the manures, the microbial community changes and becomes more homogeneous across the test. And what it marks the difference is the temperature you are running the test, not the source of the manure. So the microbial communities are similar at 55 degrees independently if they get poultry or cattle manure, and are similar at 35 degrees as well independently of the substrate. So that was interesting as well to observe that the community is determined by the temperature. And now very briefly also, I want to show you a graph of when we use slaughterhouse wastewater from a local slaughterhouse. And here what we did is we tested 3 different temperatures. They wanted to see if they could operate an anaerobic digester more at lower temperatures. That will be at 21 degrees. So we had this BMP test set at 3 different temperatures. As expected, at 21 degrees, of course, you get methane production. It's not inhibited, but you get a very low kind of production rate. So that was not recommended. And then we observe a similar behavior as observed with the manures, a lag phase with the 55 degrees, and then a straight production of methane at the 35 degrees. And here we calculated the free ammonia present at the different temperatures. As mentioned before, despite you have the same amount of ammonium, depending on the temperature, it also changes the free ammonia. So here we calculated the free ammonia concentration of 220 milligrams per liter at 53 degrees. Literature has been reported inhibitions occurring already at free ammonia higher than 40 degrees, and therefore we got this stop on the methane production at a much lower methane production. Okay, and now moving to the second example, this is more a fundamental study that we use cellulose as a substrate. Cellulose is the substrate you can use as a control of your test. When you want to know if your inoculum performs well, you set up a BMP test only with cellulose because you know how much methane you have to get. So for that test, we use that test because we wanted to test the effect of graphene oxide and reduce graphene oxide in an anaerobic digestion process. So that's a project we had with Elena that ran for the last 3 years. And the background of this project is that this graphene oxide, which is relatively cheap to obtain from graphite, is this hydrophilic material. It has oxygen functional groups and is not conductive. So you're wondering, so why to add it with an anaerobic digester? And that's because when you mix it with anaerobic microorganisms, these ones are able to reduce this graphene oxide and change their properties. So it becomes hydrophobic. It doesn't have any oxygen functional groups. And the most interesting, it becomes conductive. And that's very good for these microbes. As I mentioned earlier, you have different groups of microbes during anaerobic digestion. They have to exchange electrons. And therefore, the process, it's quite slow. So research has been moving in the last year on how to get this process a bit faster. And that's a way. You use this conductive kind of network together with the microbes that they're using to exchange electrons. And therefore, the rates go higher. So for that, we set up this test. That's a summary of the test we did. We use inoculum substrate ratio of 2. And then we set up the control test. That didn't have this nanomaterial, the GO graphene oxide, RGO reduced graphene oxide. And then we use also pharmaceutical compounds. So we add a mixture of pharmaceutical compounds at the beginning. We wanted to see how was the degradation in the presence of this nanomaterial and cellulose as substrate. And then depending on the test, we add GO or RGO. And these tests were run in a kind of fed batch mode. What does it mean, fed batch mode? It means that we set up a BMP as typical BMPs at the beginning. We add all of this, what is in the table, depending on the test. We add different things. But after, when we saw that methane production stopped, we add more substrate, cellulose. And then we observe what happened in terms of methane production and also in terms of pharmaceutical removal. Okay, so let's what was an interesting finding? So the first batch, meaning that is the first time, like your first BMP set, what we observe here is the control that reached to the specific methane production rate expected with the cellulose that goes around 360 or so, with reduced graphene oxide. So you can chemically reduce this graphene oxide before adding it into your BMP. We also got similar kind of productions, but then when we added GO, the methane production was decreased, and also it had a lag phase. It took a bit longer to start being produced methane. However, in the second and third batch, that changed, and that change you can see here on the tables. We see the comparison with the kinetics and with the methane production. So what we saw at the first test, as I mentioned it, was the methane production for the test with GO was lower, but we could already see that the rate, the MUMAX, the rate that methane is being produced, was starting to be a bit higher on those tests where the nanomaterial was added. In the third batch, when the nanomaterial is already reduced and incorporated in the biomass, so the biomass can use it to exchange electrons among the groups, we can see that this MUMAX is much higher in those tests where you have graphene oxide, independently if it's biologically reduced or chemically reduced. And also, we don't see a decrease on the methane production rate, which is also very good. So we obtain the same specific methane production rate, total production. And the fact that increases the rate is useful because that means that you can, when you think in a full-scale application, it means that, you can reduce the volume of your anaerobic digester, or alternatively, you can increase the loading. And that's good. Also, in this particular case, we wanted to monitor the kinetics of the micropollutants, how they were behaving across the BMP test. And for that, we had to run more bottles in parallel. So we had these 3 bottles for methane production that were not open at all. And then we had 3 more bottles in parallel, same conditions, to extract the samples for the pharmaceuticals. And with that, we could get the behavior, which I'm not going to go now into detail of how they behave, but what we observe in general is that it was an enhancement of biodegradability on some of these pharmaceutical compounds when the nanomaterial was added. And with that, I think that I would like to finish with the main conclusions. BMPs are very, very useful. It's relatively simple and low cost to establish this kind of sets in your lab. You can determine the maximum methane production from different organic substrates and also the kinetics of your process. That also they allow you to assess if a particular substrate will inhibit your anaerobic inoculum and how to deal with it when moving to continuous operation of anaerobic digester. And then you can easily complement them with other analysis if you can. Then that will give you this extra amount of information that normally for scientific publications are quite useful. But of course, you need to have special considerations follow, and we normally have this protocol of this paper being published when setting up your test in order to get reliable data. And with that, if you have any questions, I will be very happy to discuss. If I can also share this paper if you don't know it. And thank you very much for your attention.
Optimal sample substitution. Why did you choose 2? For example,
the 2 is the one that is recommended in this protocol, but that will depend a lot on the concentration of your substrate, of the organics of your substrate. So you can play a little bit, but we have been doing tests with 1 and 3, depends on the substrate. But when you move farther out from this, the results are not good because you have very little amount of inoculum, for instance. So it's always better if you have very concentrated substrate, try to dilute it rather than using very small amounts of inoculum just to keep the ratio, because then you have a lot of error on the way of the setting up of weighting the inoculum. Yes. We had a lab scale running in parallel continuous system that was treating municipal wastewater because was for anaerobic treatment rather than to get biogas it was anaerobic treatment of the wastewater. And then what we use is these last experiments were graphene oxide. We tested those first in the batch mode with this BMP, and then with the concentration that was working the best, we apply it in the lab. Yeah, because if you detect some disturbances, it's much better to first test it at the batch test, then you move to
Okay.
yeah.
Treatment, in a circular economy principle, and now we're talking about salaries. For example, on the municipal wastewater treatment plant, if we remove the salary downstream in primary treatment facilities, that different ways primarily recovered, how that affects maybe later anaerobic digestion. It's like you are weakening the substrate, or in a poultry or cattle, maybe you remove nitrogen from the urine, maybe from that stream. After what the digestion, then don't have it
in the digested.
That's not anyone before that kind of explanation, and what influenced the decision.
For sure, you have some guys on life cycle assessment that assess you the overall concept of now they don't call it wastewater treatment plants anymore. They call water resource recovery facilities. At the end of the day, the aim of those facilities are to treat wastewater. Let's make it clear. And then, of course, let's treat wastewater while we can recover. If you can recover stuff upstream, for me, it's better than going through the treatment and then moving to the anaerobic digestion. So if you can recover stuff before going to the treatment plant, as a pre-treatment, then you will have less sludge being produced, and therefore maybe your anaerobic digester won't have as much biogas as it. But in terms of what I want, yes. Depending on what you want to achieve. But whatever you can recover before it enters the wastewater treatment plant, for me, it's much better because it comes more concentrated there, everything gets diluted, and then you need several processes to remove stuff. In terms of nutrients, the best is to, if you can, remove them before. Yes. Yeah, sometimes you need the carbon to remove the nutrients. Yeah. Because it's very fancy to talk about, let's do an anaerobic treatment first, and then we put an anamox partial nitration. Yeah, but then implement an anamox at mainstream. It's very difficult. So it always depends on your goals and what you want to achieve.
Independent, you cannot do general.
But the anaerobic treatment now is everywhere again.
The new ways. And
anaerobic treatment for the mainstream process is also challenging. You work at lower temperatures, so you get a lot of dissolved methane that will end up in your effluent and then will end up loose and also increasing your greenhouse gas emissions from the plant. So it's always a trade-off here.
Thank you.
Yeah. Any questions from the back? Ladies. The youngest generation. Okay, silence. Very good.